So let me try to continue the example that we were doing last time, which was trying to find the number of circular permutations of a multiset. Problem: find number of circular n permutations of a multiset of k elements which will have infinite repetition, infinity a1, infinity times a2, infinity times an. Okay, so as an example, let us look at n is equal to 4. Oops, this should be a k. Size infinity times a k. Okay, n is equal to 4, my k is 3, and I'm going to call the set as what I referred to before, A, B, C in class. Okay, then I can see there are three kinds of permutations: A, B, C, A, B, C, B, C, and A, 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 A. And why are they of three different kinds? Well, let us look at the period of these examples. What is the period? How many times do I need to turn it to get it to look exactly the same? If I turn it once, I get A, B, C, right? Starting from the top, which is not the same as the original, and I need to turn it 4 times to get it back to the original state. Compared to that, I need to turn this only once, twice, and this one only once. Keep in mind, period always has to divide n, because after n turns, you're always going to come back to the original. Okay. If I look at the ordinary n permutations instead of the circular n permutations, ordinary n perms, then they are basically made by filling out n slots, and each of them have n slots, each of which has k options, right? K options. And so the total number of such permutations, therefore total number of n permutations, is equal to k to the power n. Now let us look at how many of these n permutations, normal n permutations, map to the same circular permutation. Okay. Well, I'm going to map them by n perms to circular n perms, my mapping x1, x2, xn, around the circle with x1 at the top. Okay, so it's going to look something like this, xn. Okay, then there are 4 permutations that map to ACBA that we saw initially. ACBA, CBAA, BAAC, and AACB. Right? All 4 of these actually map to this one permutation ABCA, because that's just whatever you get from these on this side is just going to be a rotation of ABCA, which in terms in a circular rotation, circular permutation, does not matter. Compared to that, for BCBC, I only have 2 choices: BCBC and CBCB. Both of these are getting mapped to BC, and for AAAA, my only choice is actually AAAA. No other permutation is going to get mapped to AAAA. So we instantly see that not the same number of permutations are getting mapped to a circular permutation, which is different from what we had when we were looking at circular permutations where each element was used only once, right? Therefore, what we get is, um, we observe number of n permutations that are mapped to any circular permutation that map to a circular permutation theta is equal to the period of theta. Oops. Period of theta, right? Which we can see from what we did before. There were 4 things mapping to AABC, 2 to BCBC, and 1 to AAAA, and that matches up to their periods that we saw before. The period of AABC was 4, period of BCBC was 2, period of AAAA is 1. Great. Let me denote by C and D the number of permutations that have period D, the number of n permutations, number of circular n perms with period D. Okay. Well, every circular permutation has some period, at least n, and as I mentioned before, the period has to divide divide n. So I get that, well, every circular permutation has some period. If I count all the circular permutations by their period, there has to be all the circular permutations. I'm going to denote by Cn the number of all circular permutations, and Cn should be equal to Cnd, summation Cnd. What else do I know? Well, look at a D permutation. Suppose it has a period less than D. Suppose it has a period, let's say E, right? Then there are E normal permutations that are getting mapped to a circular permutation C of length D, right? So every normal permutation gets mapped to some circular permutation, and E of them map to the same circular permutation of length E. So we get E times C and E is equal to k to the power D, which means, in particular, therefore, for every D dividing n, D times C and D is equal to summation E divides D mu of D over E k to the E by Mobius inversion. By Mobius inversion, as we discussed in class before this. You can find it in Dr. Terwilliger's notes, which I have posted online, at least the link to it, okay? Or you can look up in the book. This is just a brief sample video. I won't focus too heavily on this section, so you should know it, but I won't stress too much. Well, therefore, C of n is equal to 1 over D summation E divides D mu of d over e, oops, d over e, k to the e, right? I'm dividing both sides by d here. And I know that, oops, this should be c and d, and I know Cn is the sum of C and D's, therefore Cn is equal to summation n divides d C and D, which is equal to summation n divides d 1 over d summation e divides d, not n divides d, d divides n, my bad. D divides n, d divides n, 1 over d summation e divides d, mu of d over e, k to the e, okay, which is equal to 1 over n summation d divides n over d, right? Multiplying outside and inside by n and 1 over n so that the sum total remains constant. E divides d, mu of d over e, k to the e. Okay, well, I can rearrange these terms, right, to say this is the same as 1 over n summation e divides n, because if e divides d and d divides n, then e of course divides n, right? K to the e summation, well, now e has to divide d, which has to divide n over d, mu of d over e. Okay, I don't like this e divides d divides n. What I'm going to do is going to create some new alphabet. Okay, I'm going to simplify, write this term sum in a simpler manner as summation d divides n d mu of n over d, where my capital D is equal to, well, n over d, right? So that this becomes n over d, and my capital N is equal to n over e. So if d is n over d, n is n over e, then big D does divide big N, right? Which is why this makes sense. And if you do this, d divided by n, you get small d divided by small e. It's easy to cross-check. Okay, so I do get that this sum is this, which is, in fact, by definition, equal to phi of n, which is actually equal to phi of n over e, because capital N is n over e. And so I can write this big cumbersome sum as 1 over n summation e over n k to the e times phi of n over e. Okay, and that allows me to say theorem for n greater than or equal to k greater than or equal to 1, the number of circular n permutations, the number of circular n perms of the multiset infinity times a1, infinity times a2, all the way to infinity times ak, which I'll denote by maybe Cn, is Cn is equal to 1 over n summation e divides n phi of n over e k to the e, where phi of n is equal to Euler-Toten function, Euler phi function or Toten function of n. Okay, so this is my first test video. Let me know if you're having trouble following it. I'm going to post these notes online. Also, by the time you see this video, the notes should be up with it. Hopefully, you'll be able to follow them together. Okay? Let me know if you have any trouble, suggestion, anything. Okay? Best luck. Let's get through this together.